Hello everyone and welcome to Mathematics Tutorial 7, the second lecture in our powers series. Before we move on to the next topic then, there's one more powers lecture after this. Today I want to consider exponential functions for you to become comfortable with performing calculations that use exponential functions, for you to become comfortable in the use of logarithms, and for you to be able to manipulate logarithms when you see them in equations. And this will all lead into the final powers tutorial, where we are going to look at graphical representations and how we can use these concepts to linearize relationships that may not first appear as linear. So let's imagine a chemical example. Let's imagine the nuclear decay of uranium-235 that happens when a uranium-235 atom is hit by a neutron, which causes it to split, and upon splitting, each of those atoms emits 3 more neutrons. So it proceeds in an exponential manner, with the number of released neutrons growing with time. And the numbers of atoms that are splitting and the number of neutrons that are produced obey a very simple function, that is y equals 3x, where y is the number of neutrons, which grows, as you can see on the graph there, exponentially with time. X is the number of atoms that have been split, and 3 is an experimental constant, and it's 3 in this case because we know that each atom that is split will release 3 neutrons. So there's an example of an exponential relationship there. And you'll note the rate increases as the number of atoms split increases. Now, we usually use the term, exponential growth, but in fact, it's usually reserved for a special type of function. And that function involves e, which is a natural constant and is an example of an irrational number. And an example of another irrational number is pi. What that means is that we can't express its value completely by writing it as a decimal number. So we can write a figure, it's to 4 significant figures in this case is 2.718, but the number is irrational, just like pi, and it keeps going and going and going. You will see many equations that are encountered in chemistry that have these exponential functions. So I show the exponential function here in red. This is the Arrhenius equation, and some of you may remember this from school. Here, exp or e is an operator, and we can use the two terms interchangeably here. Sometimes you'll see it written as just e, other times you'll see it written as exp. It tends to be written as exp in chemistry because often the term after exp can be quite large, so it just makes the equation look tidier if you use exp. The term in brackets there we call the domain. This is the thing that is raised to the power of e. So this is the e to the x term here. So that whole term in brackets is called the domain. The rate constant here, K, then, is our observed variable, and temperature is our controlled variable. So if you look at that equation, A is a pre-exponential factor, EA is the activation energy for the reaction, and R is the gas constant. T is our controlled variable. But really what we're saying there is that the rate constant has an exponential dependence on temperature. Let's have a look at a worked example then. I want to just discuss how we calculate the exponential of a number using your calculators, because it can sometimes be a source of confusion. So most of you have probably got scientific calculators and have been using them probably in A level. There are some great scientific calculators out there. I recommend the Casio versions. The question asks us, what is the exponential of 2.5? Well, on most pocket calculators, the exponential key has this symbol here, e to the x. And you type in 2.5 and you press the e to the x key. And the number that comes out is 12.18. Note that sometimes on some calculators that step needs to be reversed. So you press the EX key first and then type in 2.5. Of course, we can also perform these kinds of calculations using Microsoft Excel. So in Excel, you just open a window, you open Excel and you find a box and you simply type equals EXP 2.5 and you hit return, and Excel will calculate the exponential of 2.5 in that case. The EXP function in Excel is not case sensitive, so it doesn't have to be in caps lock. So I want you to get comfortable with using that exponential term on your calculators. So here's a form of the Van Hoff isotherm. K equals the exponential of minus delta G divided by RT. And I would like you to determine the value of K, the equilibrium constant here, when delta G is equal to 4 kilojoules per mole, and you're given the other terms in that equation there. Calculate that using your calculators, and then for 1.2, repeat the question, but use a different value of delta G this time, minus 12 kilojoules per mole, and we'll go through the answer on the next slide. Okay, so first 1.1 then. We take our Van Hoff isotherm equation, and you can see that we've got every single parameter in that equation. We have delta G, which is equal to 4 kilojoules per mole. We have a value for the gas constant, which is 8.314 joules per Kelvin per mole. And we have a value for temperature of 298 Kelvin. And we're trying to calculate the equilibrium constant K. So we plug the numbers into the equation, being slightly careful here because we can see that we were given delta G in kilojoules per mole here, but we need to convert that to joules per mole because our gas constant is in joules per Kelvin per mole. So we've got to keep the delta G value here in consistent units. So we just convert 4 kilojoules per mole to 4,000 joules per mole. And we plug these values into our calculators, and the value you'll get is equal to the exponential of minus 1.614. And you'll notice that all of the units cancel out here. So this equilibrium constant is dimensionless in terms of units. And the value is 0.199. If you didn't get that, it's likely that you didn't convert the 4 kilojoules per mole to joules per mole. So don't beat yourself up. Have another go at 1.2 and see if you get the right answer. One sort of little tip here in terms of examinations in chemistry, when you come to either perform problems in your coursework or problems in an exam, make sure you write out every single step of your calculation, just like I have here. And I know that your teachers have been telling you this probably since year 7 or 8 in mathematics and the sciences, to write out every single step in your calculation. But it's really, really important that you do it. I don't negatively mark. So if you get the wrong answer, you don't actually lose marks, right? You don't gain the mark for the right answer. But if your steps up to the calculation of an answer were correct, then you will always gain some marks, even if you got the wrong answer. So it's very, very important that you show your workings and demonstrate your understanding of the calculation in question by showing your workings. Okay, and that value for 1.2 was 126.9. Okay, what about the inverse of exponentials? We have this exponential function. How do we manipulate it algebraically or in an equation? Well, the inverse function to the exponential, that e to the x, is a natural logarithm. So if we have a value e to the x that is equal to y, an equally valid expression is the natural logarithm of y is equal to x. So we can solve for x when we see an exponential function in an equation. Let's have a look at a worked example. We're asked to rearrange the Van 't Hoff isotherm to make delta G the subject. So here's our Van 't Hoff isotherm that we saw in the self-test a couple of slides ago. And we are trying to make delta G the subject. So the first thing that you know is that we have this exponential function that we need to deal with. And this is the first thing that we're going to deal with because the term in brackets is in brackets. So it's the last thing that we would deal with in our BODMAS scheme, if you remember that from the algebra maths tutorials. So let's inverse that exponential function by taking the natural logarithm of both sides. Now, we take the natural logarithm of an exponential function, and that is equal to x here. Okay, so you can see that I remove that natural logarithm by simplifying the left-hand side of the equation. So I've taken the natural logarithm of both sides. The natural logarithm of e to the x, or in this case, the exponential of minus delta g over rt, is equal to just x, where x is minus delta g over rt. And I remove the exponential function from the left-hand side of the equation. In the next step, my delta g term is divided by minus rt, so I can multiply both sides by minus rt here, and I end up with the final result with delta g as the subject and equal to minus rt times the natural logarithm of k. Another worked example then involving some kind of rearrangement. This one from an example using reaction kinetics. So at the start of a reaction, the concentration of reactant is R0. During the course of the reaction, which occurs via first order kinetics, the concentration of R decreases with time according to the rate equation here. RT equals R0 multiplied by the exponential of minus KT. So you'll note then that here exponential is presented simply as E. In that equation, RT is the concentration of reactant at time t, after the reaction has started. K is our first order rate constant. We're asked to rearrange the equation to make minus KT the subject. Now don't panic if you don't understand the reaction kinetics here. That's not the main focus of these mathematics tutorials. We will study reaction kinetics in physical chemistry lectures in the first year. So we don't need to understand all of the reaction kinetics. All we need to do is look at that equation and make minus KT the subject. So again, remembering the BODMAS scheme, we want to deal with the multiplication first. And you'll remember that when we're rearranging or when we're unpicking an equation, we prioritize the BODMAS scheme in reverse. So it's subtraction first and brackets last. So the exponential function would come under the of letter in the BODMAS scheme, and multiplication comes before that when we're rearranging an equation. So we notice that our exponential function, or the exponential of minus kt, has been multiplied by r0. So we want to get rid of that first. We want to move that r0 over to the other side of the equals sign, the left-hand side of the equation. So we first divide both sides by r0, and we are left with RT divided by R0 is equal to the exponential of minus KT. Now, minus KT here is the domain of the exponential, So we can take the natural logarithm of both sides. So the natural logarithm of RT over R0 is equal to the natural logarithm of the exponential minus KT. We know, therefore, that the natural logarithm of e to the x, or e to the minus kt, is equal to x or minus kt. So we are left with an expression whereby minus kt is the subject and is equal to the natural logarithm of rt over r0. Now, we can express numbers to other bases other than e. So we've been looking at e as a base here. All we need to write is a to the x, where a is a constant. We've been looking at e to the x, where we use this base of e, which is equal to about 2.718. Here, we can understand that we can have logarithms in other bases as well, right? Just like we saw with the very first example at the start of the lecture, where y was equal to 3x. Well, our base there was 3, or our constant a was 3. A very common example that you'll come across in mathematics and chemistry is where y equals 10x, where we have a base of 10. And the inverse to 10x is logarithm, or log, to the base 10, which we symbolize as log x. And we can convert between 10x and log x, very similar to our natural logarithms that we showed on the previous slide. If 10x is equal to y, then log y is equal to x. So let's have a look at a worked example. The pH of trifluoroethanoic acid is 4.5. And from the definition of pH here, where pH is minus log the concentration of protons, we're asked to calculate the proton concentration. So basically, we've got to solve for H plus here. We've got to make H plus the subject of the equation. The first thing we do is multiply both sides of by minus 1. What that does is it shifts the negative sign over to the pH side of the equation, because we can't take, we want to move the negative sign over to that side of the equation. Now we want to remove the logarithm. So we perform the reverse operation to both sides. The reverse operation to log x is 10x. So we take 10 to the power of minus pH is equal to 10 to the power of log h plus. But of course, we know that that will remove the logarithmic function from the right-hand side of the equation, and we're left with an expression whereby h plus is the subject of the equation and is equal to 10 to the minus pH. And when you plug the numbers in here, whereby the pH of trifluoroethanoic acid is 4.5, you get a value of 3.16 times 10 to the minus 5 moles per decimeter cubed. That's the concentration of protons when trifluoroethanoic acid is pH 4.5. So in this self-test, you are asked to rearrange to make x the subject. So you're just taking the inverse operation in each case, and I'll go through the answers in the next slide. Pause here. So here are the answers. Hopefully they're quite simple. Some involve just a simple single inverse operation. Others involve you to think a little bit more. There are some laws which govern logarithms, and we'll go through those now. Law 1 is that log a plus log b is equal to log ab. So if you're adding logarithms, then you can express them as a single logarithm, whereby you multiply, in this case, a and b. If you're subtracting log a minus log b, then that is equal to log a over b. And if you have log a raised to another power, so log a raised to the power of b, that's equal to b times log a. And you'll note then that I've written all of these in terms of log to the base 10, but these are equally valid for natural logarithms or any logarithm that's expressed in another base. So use those laws of logarithms which were on the previous slide and simplify the following equations. So I'll go through the answers for self-test 3. Ln 5 plus ln 3. Well, we are adding two natural logarithms here, so we multiply the 5 and 3 to give us ln 15. Ln 5 plus ln 8 plus ln 2. Again, we can express these as a single natural logarithm, and we multiply 5 times 8 times 2 to give us ln 80. Ln 6 minus ln 3, well, we're subtracting two natural logarithms, so we know that that will equal ln 6 over 2, which is equal to ln 2. Ln 5f minus ln 5, again, we're subtracting these two natural logarithms, so we can express that as ln 5f over 5, and the two 5's cancel out to give us just ln f. Log a plus 3 log a. We collect all of the like terms here to give us 5 log a, which we know is equal to log a to the power of 5. Log b plus log b squared is equal to log b times b squared. Collect those like terms, and that's equal to log b cubed. Okay, and that's all we've got time for today. I'll see you in the next maths tutorial. Thank you very much.